Dear students, today we'll try to solve this question, which is related to one of the applications for strength of materials, which is supposed to be one of your post-class activities. So I will do it, and then possibly you can do it in different methods. So consider a simply supported universal beam. The information for the beam is 360 UB, 44.7, which is the kgs per meter length of 3 meters, the length of that beam. There is a 30 kilonewton point load acting transverse to the beam, 1 meter from the left end. The Young modulus is 200 gigapascal. Write a script that calculates the direct stress and deflection along the length of the beam. You can ignore the weight of the beam because, as I say, 44.7 is kgs per meter length, or you can include it. So we can possibly include as well the weight of the beam, just to show you the difference between them. Plot the stress and deflection along the length of the beam on the same graph. How do you create a plot with two y-axes? Because that's what we're trying to distinguish between them in these activities. All right, so the things which you could need as well, I will share the screen to show you. If you use some of the you go to resources in the Moodle, you can find this is taken from the machinery handbook formula sheets. You have a different formulas for beams. So as I say, is a simply supported universal beam, supported from two ends, and there is a load at some points from one of the ends, left ends or right ends, whatever is the same application using for it. So this is a supported, and there is a load applied at that point here. So technically, to calculate the deflection and as well the stresses, we have the equations here, which we will use and implement. That's depends on supported at both ends, load at any point, which is the category case 3, and you can find the deflection at the load if you want, or you want to find the maximum deflection to be calculated. And as well, the stress at the load you can calculate, and other important informations. We're going through it. So I'll go back and share my screen to the script so we can start scripting based on the equations we learned from strength of materials, and how can we write the script for this code. So as we learned in Matlab, we always start with CLC and clear. That's to ensure will clear for me the command window and the workspace, so will not interfere with the previous scripts I use all. As well, there is some new command which we call it close all. Close all is also if I have another figures open from previous scripts, this will ensure that this will close all the figures or everything related to my script. So if we start with first thing, beam length is the information given to us. So as you can see, it's given for this question is I use millimeters, 3,000, and you can put the units millimeters. I like to put the square brackets on it. And remember, you can really just push this above distance so you can have a nice organization for your script. I don't want to, as I say, when I don't want to display the results under the command window, I put the semicolon, and that way I'll avoid any issues to show too much information. The point load, as you can see, is stated in the question. It's about load acting at the beam 1 meter from the left. So I'll call this value A equals 1000. As remember, we say we're solving this with respect to millimeters, and I'll write the comments here. Length of short section beam, because that's where it is applied as stated in the question. So that information coming from the question itself. Okay, that one here, and we go through it. I could pull this later if it's too much, but we push it as much as we can do it. The beam weight here is the beam. I will take that into account. Beam weight for this question is given to us is 44.7, such as I read it for you, divided by 1000. That is multiplied by 9.81, which is the gravity acceleration. So that is the the transferring the units to be in newtons times what times the length of the beam, which is 3 meters. But because we could change this later, so I'd prefer you write the script to make sure it's related to the information. You even can say beam weight is the value divided by 1000, and you calculate times the gravity acceleration. That will convert that to for us as a newton, the converting it to a weight. So we call that is in newtons for its units, newton. And then I push it to the side, you can see it. Now, I saved that question as a beam deflection question. I could run that just to make sure like it's working for me. Remember, if I don't want to display results, I could really just use the comments. But you can see here, the A is 1000 millimeters, the total beam length is 3000, and the beam weight is the value, which is Newton 1.3155 kilonewtons, or 10 to the power 3 newtons. These again information given in the question itself. Now, other information given in the question is the Young modulus. You can see it here. It's 200 gigabytes, but I will tell you these things for us. To be sure with this, don't use that. I'll copy the same words for it. Young's modulus equals, and here you can put the value 200 E3. And the reason, because we want to have very close units. When you work in megapascal, there is the canceling of units. Megapascal is easy to work in millimeters. So if you work the dimensions in millimeters, similar to the length and as well the sections, it's preferred you convert everything to megapascal. 200 is times the value, which is E3, 10 to the power 3. And because giga is 10 to the power 9, so we put it in mega and we go through it. So Young modulus. Even there was Young modulus written like this, avoid that. So you see, I just make it clearly for that beam in it. That's another information given to us. Now, I will go to the formula sheet because there are a lot of important resources. Steel and tube data could help us to find some of the information. I'll just find that for us because the type of the beam, this is all available under resources. So remember, it's 360 UB. So I'll search for 360 UB. I'll share my screen now. Share screen. So this is available dimensions. So 360 UB, and you need to find the right kgs per meter. So that's the reason we divided by 1000. So 360 UB, there's 56.7. That's not our one. 50.7, no. And 44.7, that's the one stated in the question. Now it's that kgs per unit length per meter. And because we divided that by 1000 to convert it to millimeters, and then times 9.81, so we get the answer for it in newtons, the weight for that. And then you will get the question for this will be to find the Ix and the I values for it. So Ixx for this one is about 121, 10 to the power 6. I'll zoom in. So 10 to the power 6 millimeters to the power 4.1. So that is very important for this type of a question. So I will type here Ixx, the second moment of area is 121 E6 I'm using here, and that will give me the units for its millimeters to the power 4. And that way you understand where this value coming from and why we choose this. So based on the type of the universal beam, we selected the Ixx. Another things we could choose from that sheet as well is the actually Zx. We need it in the equations to calculate. So Zx for that one is Z, capital Zx equals, as you can see, it's 689 E3. Or going back to my script. I'm just showing you where we got this. And now I go and share my script again. And you can see it. So that is 689 E3 to the power 3. And the units for the Zx is will be units, millimeters to the power 3. Put as well that one. And nicely, you can all bring them to be nice so you can understand the units from them. So that is ZX, and as well, the load, point load, W, is in this question, it's given to us, which is 30 kilonewton point load. So I would say it's 30,000 because we want to make it newtons, and units for that for it we choose Newton. Okay, so we move this to that side. I could also make sure like you see the units. We can always organize that to make it looks better. Use the comma here. Units. Like you always try to organize your script to make it looks more professional and easy for people to follow and to understand what you're trying to do. All right, so now to show you, I need to go back to the formula where we will start working on it. But we'll show you the steps for it step by step and how can we calculate it. So I go and share again my screen for the formula. So this is the formula here. You have type 1, which is the supported at both ends uniform load. So that is the weight of the beam. If I want to take it into account, I could take the stress at the center or the maximum stress. But because we need to go and write a script to calculate the direct stress and deflection along the length of the beam, you can ignore the weight of the beam. So I will say at this stage, we're not ignoring, we take it into consideration. So I could remove that statement from the question, but if I don't want to ignore the beam, then technically I don't need to take the beam weight for it. So I can remove that line and make it as a comment. So that's to show you the things I've done, changes in the question itself. But in the formula sheet, so we are using this equations, these formulas, and these equations. And here you have the letter A, where I put it as about 1,000 in the question, and then I'll organize it to find. And W is the capital, which is the load, and you have the total load of the beam. So I go back to my script and show you how can we change the values and we work on it. But before that, I need to tell it to understand the beam. So total beam, which is mean the length of the beam, equals start from 0 and goes with a range 0.1 and that till end of what? The beam length. So what I'm telling the software, beam length. I'm telling the software my range, so that is to represent for me a range starting from 0, the first point for the beam, with an increment 0.1, 0.1, 0.1, till I reach to the 3,000 millimeters or 3 meters. So that is the range for my section, which we're trying to understand from it. But before that, I will show you the other information, which is very important for it. So we call that one like for us to understand it is for the section for it. Now, if you look to the formula sheet as well, so I'll go back to the formula sheet and not this one, sharing. There is also something, because I defined A here, which is the 1,000 stated, but then I need to define the B value, which is, it's based on the first equation. So how can I define that in the script? So I will come here and I say B equals, so will be the beam length, that's the beam length, minus what will be impacting on that is the A value. So that is, we write the notes here, is the length of longer, which is the 2 meters technically, section of the beam. And it's again in millimeters because I kept everything in millimeters. Push this comments here so doesn't interfere with my script. And that will be the total beam, which is related to the beam, and you go through it. All right. So Now I need to do the A segment because to tell it start from a segment to segment. So A segment equals underscore segment equals. So that is starting from 0, goes with an increment 0.1 and stops till the value of A, which is kind of, I'm telling this the beam. I'll show it again in the figure. So for A segment, I'm telling it start from this point is 0 with an increment 0.1, 0.2, 0.3, 0.4, 0.5 till you reach to the 1. And that's to calculate everything, stress and deflection around that point. Okay, go back to my script. So we have the A segment. The same thing, I could do the B segment equals. Here, B segment, I need to be very careful. So 0 is the start. I'm starting from the other end. We could do 0.1, and then that will be is B minus 0.1 because we don't want to reach to A, because remember, if it goes to B, then I will have duplicated values and I want to avoid that. So it's, if I can show you that in the figure, so I'm starting, let's say, from B 0.1.1, and I will not reach the 1 because that is related to A, so I will reach the point here just before that value. Okay, now I go back to my script. Oh, I didn't share it. So that's from here, goes till that point before reaching to A. And now I go back to script. Okay, so those are the segments which I needed to calculate. Now I need to create, to put stress. So stress is the equation I want to calculate. We could use the command called zeros, create arrays of all zeros. So I'm creating an array empty, which I will show you when I run it, to say, hey, put zeros there. 1 is, and then that will be the length, and which is the total of the beam. The comments about explaining this is stress due to point load in short section. So this is the kind of like I'm trying to distinguish for it, and you go through it. So let's show you what has happened so far when we run this script. Okay, so I'll run it. So that is stress. If I click on it, the stress here, it's technically, it's reserved for me at the points, how much points I need for it, but it gives me the values of zeros because later I will replace these zeros with the right values for it, which is kind of like trying to train the software to what we're trying to achieve in it. All right, so now stress again. It's 1 to length. Now we bring the right values. A segment, so that is the first one, equals, now we copy the equations, minus from the sheet W times B times A segment divided by ZX divided by beam length. And will give me the selection for it. So that equation is stress due to point load in long section. Sorry. That one. Yeah, sorry. That is here. I just got confused. That should be for that one, and that should be for that one. Sorry. So that equation is stress due to short section. It's taking the A segment. Now start the stress for segment. So to make it sure, the first one, as I say, is just to create the matrices for the stresses. and now I iterate it. So that is the short segment switching equation. I'll show you the equation we used from the formula on the sheet. So that is the point which we use the equation W, A, B, and Z with the length of the beam stress at the load. And now we do the same thing to calculate the stress from the long 4-segment long section. So stress here will be end minus 1 to the length and then from the length, which will be a segment, but then we put plus 1 to make sure we don't miss anything, equals the calculation for that will be minus W times A times B segment, and that's over ZX divided by beam length for it. Right. So that is the stress for it. Let's run the script and see if everything is going. So now the stress is replaced with the values to represent the stress calculated. So we kind of calculated the stresses from one end to the A and from the other end to the A again, but we're taking two different segments for it. Okay, these two are due to what we call it is the stresses due to point loads in a short section and the long section. Okay. Now we need to add the stresses. So we say stress equals stress minus beam weight divided by 2 divided by Zx divided by beam length. That one adding in stress due to self-weight. So if we say ignore self-weight, that step I don't need to do, but we just say let's do it. So weight of the beam. Okay, so that is the script to add the other stress. So now when I click on that, I should get, I could really just not show it there. And then you can see the values now with the stress is changed to include the self-weight of the beam. All right, that's all related to the stress. So I could write here, comment, comment, stress calculations. Now we do another comment is deflection calculations. And as well, deflections, you go to the formula sheet and use the formula sheet. So y equals, we put y representing as a deflection, and we put zeros, like to just say, book me these zeros for it, 1, and that will be the length of total beam. So when I come to the deflection here, again, what I did, I just added zeros to make sure I'm okay with my calculating the deflection. So that will write for this line. It's how can we use that to just create it. Now we need to calculate the deflection to each one of them. Deflection is exactly the same what we did in the previous things, but we will write it again in a new script. So we will have here y is the deflection represent for us, and we want to the length and A segment. And for that deflection, we need to include the equation. So it will be equals W times B, but because we have different values for B as a matrix, and A segment divided by 6 based on the equation, divided by Young modulus. I'll copy that to make sure it comes the same, divided by Ixx, the second moment of area, and then divided by beam length with the dot because there are multiple values, and that will be beam length square. This equation is longer because I'll show you which one in the formula, minus A segment dot, that will be square, minus B square, but B, we'll go through it. So that is technically what we call it. I will put the comments here. Deflection due to point load in short section. I could put that comment on top of it so you can see it in one line. So deflection due to that point, and you can go through it. So let's see where this equation came from, the formula sheet to calculate the deflection for it. So that equation, it's slightly, especially the beam length squares minus A segment square and then minus B square. It's a long equation which you can be. So if I go and share the formula here, you can see it in the form already on the formula sheet. It's technically I use this formula here. So I use this one, which is the formula related to that deflection. Now I go to the script again. So that's how my script looks like for deflection. Okay, now if I run it, I go and find the deflection. Instead of 0 values, it's brought me the right deflection values. Okay, so that is deflection due to the point in a short section. Now I need to do the same thing as the deflection due to point load in long section. So I will just copy that one and put it here, and I say due to long section. Okay, and for that section, it's required me to do the equation, which is the same as we did for the stress, but here we call it y, and we will do end. So starting from end, minus 1, and that will be to the length A segment plus 1, and then equals W, the load, times A times brackets is B segment, and that is divided by 6, divided by Young modulus and Ix, and I can select the beam length and beam length square till here because I need to change a few things as stated, and then that will be minus B underscore segment, but that because multiple points square, and then minus we have the A square, and we close the brackets. So that is technically, we calculate the deflection. I run it now and should be updated for me, the deflection from taking into account both ends for that way. So now since we have it, we need to add including the deflection due to self-weight. So we put the comments here, deflection due to self-weight of the beam, because we need that, and that will be to add them. So we will add them. So we could say adding the deflection due to self beam. So y equals y plus, so the last y we calculated the deflection, beam weight, we can select it from here, dot times total beam dot times brackets beam length. This is all as well from the equation, minus total I misspelled total, so it would be total beam. Yeah, total beam. So if I spell total beam, it should be misspelled again. That cross the brackets divided by 24 divided by Young modulus. So I need to copy this. IX beam length till here. So following the equation, and that would be beam length square and plus, it's a long equation, but we just follow it very carefully. Total beam, as I spelled, as I say, spelled wrong, so we keep with that misspelling. I could correct that later, it's just typing. And then you have the beam length minus total beam, and then brackets, and we close that. So that is technically, we calculated the total beam for the weight. When I run that one, it should be now updating the final y value. Now, if I show you in the formula sheet, which equation is that? So that is the self. So technically, the long equation I was doing is that one, general formula for deflection at any point. So that is the deflection, which Wx, and adding to the other deflections we calculated. So one, remember, we did for segment length A, for segment length B, and then due to the weight of the beam. Let's go back to the script. Later I could fix any errors or any things when we have time, because when you script, you may get some errors and then we add them. So as soon as we found the deflection and as well the stress, we could now start figure. So we call it figure, just to give it an indication. Here we name the figure because we have two values for the x, and you have h1 and h2. The reason we're doing it that way, because you have two on the y-axis and one value for the x-axis, which is the length of the beam, and we want to make sure like we plot this very professionally. So plot y, and then we use the scale for it from 0, the range 0.1, that will finish till the beam length. So that is the length for it. And then we name this as a stress, and the stress will be 0, 0.1 to the range, which is again the beam length. And then we go to the y value and we close that. Now we could add the legend to distinguish between them. The legend is the best, is to demonstrate them how they appear the first time, stress, and the other one would be the deflection. So that is for the plot. And now we could do X label. So the X will represent for me the length. Length of the beam. And we could give it different colors. You can use semicolons here just to show them. And the Y label, we could call it, for example, stress. That stress is calculated in megapascal. And then remember, we have the other x's, x's ax2, because we have the second axis. So that is used just to handle the second y-axis, and then we call it y label. The second one will be deflection. You can add the units here in millimeters, and then we go through it. So if you ask me what is the purpose of that command, so that is to set, so let's write it, sets the current handle to the second y-axis, because we have two y-axes. And I forgot to add the first one, so I could add it after the legend. So the same thing. I could copy that just to make life easy. X's, and I call it that one 1. And that will be sets the current handle to the first y-axis. That way. Now, in my equation, I misspelled the, if you can see the total beam, I misspell it. So that should be total, total, total. And if there is any place I misspell it, I could fix that. Total of the beam. Now I check it there to make sure like it's connecting. It's possibly if I missed it anywhere, so I could go back and check it again to make sure will not give me an error. But again, we could run it and then will give me an error and say, okay, what is it going there? So it's giving me an error. You can see that I think it's line 33. So I come and check line 33. Yeah, that's the total. And you can see total beam. Now save. Line 33 is obviously there is another total here, and that's a good thing. It's like when you discover something, you find that the variable total is not defined. Yeah, that one, which is just telling you if I want to fix something, it's easy to go through it. And now it's everything run. So you can see very clearly, I could put the title as well, which I will add it later. But here you get the deflection to works from 0 to 1 with respect to this y-axis. And then you have the stress in megapascal. We could add the length of the beam. We choose in units in millimeters. So I can come back and edit my plot. So the x-axis, which we call it the stress and deflection. So length of the beam, I could add the units in millimeters. And also I could add title. We call it beam deflection. Beam stress and deflection. You could put something capital letters, it's up to you. And now we save again the script, and you can have it nicely plotted in that beam stress and deflection. And again, if anything you misspell, it's not bad to go and pick it up and correct it, like how I done it in this script, because it's good to have a script tight and clean and easy to follow. And again, as I say, anything could maybe show something you're not liking, you can have a time to fix it. You can see my valuables here, the one I've done, and the values from 0 to 3000. And you can say, but your values is reading 1 to 3001 because we needed to create that. So you can see clearly I'm really working with the range from 0 to 3000. That's the length of the beam. The point where the point load was applied at 1000. So I can check even the graph to make sure if I'm working in the right direction. So that when actually it's what's happened, the point load, and also I take into account with that the self weight of the beam. If I don't want to take the self weight of the beam, technically that extra line for stress and line for deflection, you just remove it, and that's mean you're ignoring the weight of the beam. But we're trying to get things more accurate. Another question you can come to you and say, hey, why your stress isn't negative? Because if you look to the formula sheets, it's actually our stress isn't negative here. It's always minus. So stress is center minus WL over Z. That's for in the centroid, or even at point load minus WAB over ZL. So always our stress in this type of application. And if it's UDL, uniform distributed load, use the self weight, is minus WL of 8Z. So kind of like stress at the center for it. So it's always good to know about that in case you want to be aware of its stress, the weight of the beam, and you go through this application. Yeah. So it's a very good example for you to follow. Like you want to use that one stress or that equation, the right one for you, and it can really apply for your information. I hope this like YouTube video is very good and helpful for you. Please, if you find anything you want to add, you want to improve, I'm quite sure there's a window you can improve these lines here. You can do another method, and you definitely try to test it in different ways. I hope this will help you for as well your assignment. Thank you very much.